Stereochemical aspects of nucleophilic substitution reaction. Here we are going to learn the stereochemistry of both Sn1 and Sn2 mechanism. To begin with, we have to be familiar with few important terms related to the topic. The first term, optical activity. The property of a substance to rotate the plane polarized light towards right hand side or left hand side is called optical activity. Plane polarized light is obtained by passing normal light through Nicol prism, which is a Polaroid. Second one, optically active substance. These are substances which can rotate the plane polarized light towards right hand side or left hand side. So substances which can rotate plane polarized light towards the right hand side or left hand side are called optically active substances. Third one, optical isomerism. Two or more compounds having the same molecular formula and structural formula but differing in the direction of rotation of the plane polarized light are called optical isomers, and that phenomenon is called optical isomerism. Example, lactic acid. Dextro and levorotatory compounds or DL compounds. Compounds which rotate plane polarized light to the right hand side are called dextrorotatory compounds or D compounds, or we can write it as plus compounds. Compounds which rotate plane polarized light to the left hand side are called levorotatory compounds or L compounds, or even we can write it as minus compounds. Example, D and L lactic acid or plus or minus lactic acid. Molecular symmetry. Based on symmetry, we can classify molecules into two categories, symmetrical molecules or asymmetrical molecules. By drawing an imaginary line, if the molecule can be cut into two identical halves by a plane, then it is called a symmetrical molecule, and the plane is called plane of symmetry. To explain the concept, I had taken two simple examples. The first one is 2-chloropropane. As you all know, 2-chloropropane is a symmetrical molecule. The reason is we can cut 2-chloropropane into two equal halves by using a plane called plane of symmetry. The second example is 2-chlorobutane. Now 2-chlorobutane we cannot divide into two equal halves by using a plane, because in the right hand side of the plane you can see a methyl group and in the left hand side you can see an ethyl group. So it is not a symmetrical molecule, or we will call it as an asymmetrical molecule. If the molecule does not have a plane of symmetry, it is called an asymmetrical molecule. Chirality. Molecules which are non-superimposable on their mirror images are called chiral molecule, and this property is known as chirality. For example, I had given one image over here. It is an image of a hand. As you all know, both hands are identical, but we cannot superimpose it. That means it is a chiral object. Molecules which are superimposable on their mirror images are called a chiral molecule. Here I had taken methanol as an example. Both are mirror images and I can easily superimpose it. Then we say it is an example for a chiral molecule. Chiral carbon atom or asymmetric carbon atom. The carbon atom which is bonded to 4 different atoms or groups is called a chiral carbon atom. Look at the example given over there. The carbon atom is at the center and it is bonded to 4 different groups X, Y, Z and W. Then we say the carbon atom is a chiral carbon atom. The second image is a mirror image of the first one, but both are non-superimposable. Enantiomers. The pair of molecules which are non-superimposable mirror images of each other are called enantiomers. Here I had taken amino acid as an example. The second amino acid molecule is a mirror image of the first one, but both are non-superimposable. Then the pair of molecules are called enantiomers. Racemic mixtures. An equimolar mixture of the enantiomers is called a racemic mixture. Here I had taken an example of lactic acid, L-lactic acid and D-lactic acid. If the percentage of composition of L-lactic acid and D-lactic acid are 50% each, then I can say the mixture as racemic mixture. Racemic mixtures are optically inactive because optical rotation due to L isomer will cancel the optical rotation due to D isomer. Retention of configuration. Consider following example. This example is an example for a nucleophilic substitution reaction. Here the nucleophile is Y is replacing X. So the only change during this chemical reaction is the replacement of X by Y. The relative configurations of A, B and C are retaining. Then we can say there is a retention of configuration for the product. It is the preservation of integrity of the spatial arrangement of bonds at an asymmetric center during a chemical reaction. Inversion, retention and racemization. Consider the following example. The carbon atom at the center is an asymmetric carbon atom. This particular molecule is undergoing a nucleophilic substitution reaction. There are 3 outcomes for this reaction. Either you can get product A, or you can get product B, or you can get a mixture of A and B. What is the importance of product A? The configuration is retained over there. But in product B, the configuration is completely inverted. And under C, you have 50% of A and 50% of B. Then we can say product A has a retention of configuration, product B has an inversion of configuration, and product C is a racemic mixture. So whenever nucleophilic substitution reaction happens, the products will have either a retention of configuration or an inversion of configuration, or we may get a racemic mixture. Stereochemical aspects of Sn1 and Sn2 mechanisms or reactions. Now we are going to learn under Sn1 and Sn2 reaction what is the configuration of the products what we are going to obtain. Sn2 reaction. The mechanism for Sn2 reaction is written over there. It is a single step mechanism. Hope you all remember it. Here the nucleophile, which is the OH- ion, is attacking the carbon atom from the opposite side of the leaving group. Here the leaving group is the halogen atom. Here it is bromine. Now the configuration of the product is completely inverted. That means the product has inversion of configuration. So under Sn2 mechanism, the products what we obtain will have an inversion of configuration. Sn1 reaction. As you all know, in Sn1 reaction there are 2 steps. The first step, a carbocation will form, and in the second step, the carbocation will changes into product. The carbon atom in the carbocation is sp2 hybridized. That means it has a planar structure. Therefore, the nucleophile can attack the carbocation either from the front side or from the back side in the second step. Hence, it results two different types of product. One set has an inversion of configuration and the other set has a retention of configuration. Both sets will be 50% each, and hence we will get a racemic mixture. Meaning, under Sn1 reaction, the product obtained will be a racemic mixture.